We want to find therapies for complex diseases like Parkinson's or heart disease, but animal models are just not good enough to study the human body. We need to zoom in on human physiology. How can we do that? Starting with only a sample of blood, scientists can isolate common waste cells and genetically reprogram them into induced pluripotent stem cells. From here, different organ-specific cells can be made, such as brain, gut, and heart cells. However, since we want these cultured cells to behave as if they were in a real organ, we need to give them a different environment than the standard flat, rigid cell culture materials. Organ-on-chip devices mimic the native environment of the cells, including 3D topology or physical stretch and strain. For example, the heart muscle cells shown here are now experiencing the cyclic stretch as they would experience in our body during every heartbeat. It is a miniaturized version of our own heart, on which new drugs can be tested for efficacy and safety. Many organs on chips have been developed in the past decade by us and others, but unfortunately all require a different user-tailored control and readout system. Often these systems are bulky, and they are almost always incompatible with each other. To enable biologists and chip developers to focus on making new organs on chips instead of control and readout systems, we introduce the Translational Organ-on-chip Platform, or T.O.P, where we standardize the way organs on chips are being controlled and analyzed, without compromising user or developer flexibility. T.O.P makes life easier with active switchable integrated microfluidics, which can be used to control the fluidics from, to, and within the chips. So what does that mean for you? As a chip developer, you don't need to worry about how to drive the microfluidics or read out the sensors of your device. You simply adhere to the few design rules we provide, and your new chip becomes plug and play for the biologist. As a biologist, you can run your biological protocols automatically with the click of a button. You just select the chips you have clicked into the system in the way you see fit, set the parameters, and hit Start. Let's take a look at an example. If we would like to study the effect of a certain mixture of drugs on the heart, we insert a mixing device and two heart-on-chip devices with integrated force sensors. In the software, we select the two chips, and for each chip, we define a different mixing protocol. Automatically, the correct mixture is routed at the right time to the right model. A typical chip does not contain one organ-on-chip chamber, but rather tens of chambers, allowing a highly parallelized, high-throughput assay for many biological applications. Whether you're a developer or a biologist, let T.O.P make your life easier and provide you with the infrastructure to make your organs on chips plug and play.